So we brought in collisions at angles, and Kohei, most of the most interesting collisions are at angles, not in a nice straight line. Curling is a great example. Now, the only issue with curling is the rocks all have the same mass. So often I'll give you a curling question because of the ice, there's no friction, but you'll see, just to make it mathematically interesting so that the masses don't all cancel, I'll give them different masses. But there's beautiful physics in curling. Or here, a 10-kilogram curling stone is sliding along. Oh, sorry, I should read the whole thing. Note, kinetic energy is only conserved in a perfectly elastic collision. You know what? I told you don't worry about this perfectly elastic, so you can scribble out the word only and you can just say never. You always lose some of your kinetic energy. I'm not saying you lose total energy. I'm saying if you've lost kinetic energy, it got transferred probably into heat or in a car accident into deforming the metal. What is always conserved? The next line. And there's one more thing. This is why, in many ways, momentum is a more useful tool for analyzing stuff. The only problem is because it's a vector, it's a lot more work. With energy, you heard me often say, we're going to ignore the sound and the heat and the dissipative energy. Those are just tough to deal with. Momentum, though, is pretty nice. Curling. A curling stone is sliding across the ice when it hits a stationary, I'd probably underline the word stationary, 18-kilogram bucket of sand. After the collision, the curling stone's velocity is east, and the bucket has a velocity of 2.3 meters per second at 43 degrees south of east. Hey, are there angles in this question? Okay. What's this question asking me to find? Before the last word. What? Did you say collision? This is a job for conservation of momentum. Right? So I'm going to start out, Spence, same way. The sum of all the momentum initial. Did I leave you guys the whole page to do this one? You're going to need it. This is, I think I told you last day, the second longest in terms of math and writing and difficulty question you'll have all year. Rocket science is the only one that's longer, but at least the rocket science, it's a bit more repetitive and there are some shortcuts if you're good on your calculator. Here, you get what you get. Before the collision, how about C for curling stone and B for bucket? Before the collision, what's moving? Mass C, mass B, both or neither? Momentum of object C. Where they collide? After the collision, what's moving? Mass C, mass B, both or neither? Both. Stuck together or separate? Oh, I should have said C initial and then C final. B final. Are there angles? Oh. Okay, we can pull this off. Did they give me compass directions in the question? I'm going to draw a compass rose over here somewhere. And that north looks like a weird W because I, for some reason, added a little tail. So let's do that better. Okay. Do I know what the curling rock looks like initially coming in? Nope. No. Okay. Here's my high-tech system then, Vikas. I don't know. Wham, they collide. I hope that means they told me the other two and that I can add them tip to tail and then figure out what the incoming must have looked like. I hope. Momentum C, the curling rock after the collision, what direction? East, so I can draw an arrow like this. How big? Mass times velocity. Oh, I can do it in my head. 10 times 3. Kyle, in your head? Don't you feel a little really proud there, eh? Plus, Kyle, I'm going to pick on you, not to make fun of you, but to walk you through. I'm going to ask you to the bucket. What angle did they give me for the bucket? What angle in degrees did they give me for the bucket? And now read me the what of what? What of what? South of what? South of what? What am I going to draw first? East? You've had done that dance with me before. What of east? Which means I'm going to go down. How many degrees? Okay, which is almost close to 45, so about like that. How big will that line be? Mass times velocity. What mass? The bucket. 18 times 2.3. Kohei, mass times velocity. You know what? I need a calculator for that one. And I'm not going to round off at all because I'm using this. I'm going to keep every sig fig if I can. 18 times 2.3. 41.4. I got a hankering to add these two vectors. Any thoughts on how I might want to do this? And I'm going to draw a really big triangle over here. Nothing small. I find if I draw it big, I just make less mistakes. I always try and draw the easiest vector first. What's the easiest vector? So I'm going to draw the 30 first. The second vector, is it bigger, smaller, or the same size as the 30? Bigger? Way bigger or a little bit bigger? Okay, so how about ish? And that is 41.4. Hey, you know what? I now know what the initial momentum of the curling rock must have looked like. It must have looked like that. You know what? Well, I looked and I said I'm going to draw a nice big one. Then I said I got room. I'm going to draw it even bigger. I left the whole page. Yeah. Okay. Kyle, it looks like the angle that they gave me was this one. Yes, which I think. Don't write this down. I think would be that one. You okay with that? How big is that angle? How many degrees? 43. Is that in my triangle? No. Now look up. I cannot use the Z trick because this is not a Z. A Z has to have the top and the bottom parallel. So unfortunately, the whole Z little dealio ain't going to work. But wait. What is this form right here? A straight line. How many degrees is a straight line? 180. How many degrees is this right here? So how big must this angle be? How could I calculate it? 180 minus 43. 137? Double check me. So, common mistake, Alex, kids just barf the 43 in there. The reason I try and draw these roughly to scale is hopefully if you drew the triangle like me, you would look at that angle and you would say, wait a minute, there's no way that's 43 degrees, because 43 is close to 45. It's about that big. This thing's huge. It's got to be bigger than 90. I hope. Speaking of 90, is there a 90-degree angle anywhere in this triangle? Or, in other words, can I use SOHCAHTOA and Pythagoras? It's going to be cosine law and sine law. Which one? Cosine law or sine law? Cosine. And you know what? It's almost always going to be the cosine law. What is the cosine law? The cosine law says this. What I'm trying to find squared equals what I know squared plus the other thing that I know squared minus 2 times what I know times the other thing cosine of the angle inside the triangle. That's how I've memorized or interpolated the cosine law for years. I know you have it on your formula sheet and you can certainly use that, but I always just remember I want what's across from the angle, and it's going to be squared minus 2 times angle, cos. And I can remember it's cos because it's called the cosine law. I'm going to go straight to my calculator. 30 squared plus 41.4 squared minus 2 times 30 times 41.4 times cosine of 137. Double check for typos. I think that's right. What? Oh, and square root, because this tells me the momentum squared. And I get 66.563072. And because I'm going to use this, I'm certainly going to carry 5 or 6 sig figs. I'll carry at least 66.563. You could even go 66.5631 or 07 or whatever. Since there's a 0 there, that's a nice place to stop. But 66.563. Is that right? Anybody else? Okay. So I'm going to write down the momentum of the curling rock at the beginning was 66.563 kilogram meters per second. Oh, if that was what they wanted me to find, I'd be happy. Spencer, you told us. What did they want me to find? Momentum?
No.
What?
The initial velocity.
Oh, if I know the momentum, how the heck can I find a velocity? Which mass? This time, not mass of both, because it's not stuck together. This is the mass of the first one. Was it 10?
Yeah.
I think I can divide by 10 in my head. I think 66.563 divided by 10 is going to be 6.65. Right? The decimal moves over one? Okay. Otherwise, you'd use your calculator. Anyways, here we go. The velocity of the curling rock at the beginning equals 6.6, I guess, 6, if I round off properly, meters per second. That's not the velocity. What, Clay?
What's the magnitude?
Well, that is the magnitude. That's the speed. How do I make it a velocity, my friend?
Give it a direction.
Okay. Where is the red vector coming from? Here is where theta is going to be. By the way, that theta there, north of south, east of west, what of what? South of east, okay? How am I going to find theta? SOHCAHTOA? No, sorry. I think it's going to be the sine law, because now I do have a pair. Now I do know that. And so I have that pair there. Let me erase that, because that really gummed up the diagram. I think it's going to be this. Sine of mystery angle over what's across from the mystery angle? 41.4 equals sine of the angle that I know divided by what's across from the angle that I know, which is 66.563. And in fact, to be honest, since I have this stored here, I'm going to use my answer button. Kev, is this one fraction equals one fraction? It is. What can I do with that 41.4?
You can multiply it.
So 41.4 times the sine of 137 divided by, and I'm going to go answer button. Haha! Oh, wait.
Oh no.
Well, what? Oh, now I have to go inverse or arc sine, right? 25.1 By the way, if you're trying to visualize this a little bit, here's a top view as shadows. Here's the bucket. I guess the curling rock came in south of east at a steep angle, glanced off the bucket, and it ricocheted due east, and the bucket went off also south of east. Pardon me? Yeah, I'm in the way. Oh, can you not see that by way of the angle? Is that what you're saying? Or I'm in your way? Yeah, won't be the first time, won't be the last time. Okay. I don't have a good way to do it on my tablet, so I have to do it with shadows. There is going to be at least one question like this on your test where it's going to involve cosine law followed by sine law on the written section. Although, I think on your test, I'd give you a picture, which makes it, I think, a little easier. Like example 8. Find the final velocity, magnitude, and direction of object B. Here's my high-tech, handwritten, sketched quick picture. All right. Looking at the picture, does it appear that there's a collision? You know what this is a job for? Conservation momentum. Did I give you the... I did. Okay. The whole page? Okay. So, I would start out by saying, because there's a collision, Mr. Dewick. Hang on a second. My pen is acting up. So, the sum of all the momentum before the collision equals the sum of all the momentum after the collision. Before the collision, oh, you know what? Since I see angles, I'm going to go north, east, south, west. Before the collision, what's moving? Mass A, mass B, both or neither? The momentum of A initial. Yes? Good. Wham! They collide. After the collision, what's moving? Mass A, mass B, both or neither? Oh, stuck together or separate? Fancy word for separate? Oh, elastic, right? Elastic, rubber band, bounce off each other. Stuck out together is inelastic. And it's unfortunate those two words sound so much alike. Well, that doesn't bother me. It's unfortunate that anelastic and inelastic sound so much alike, because when I say it's an elastic collision, it's hard for you to tell what I just said. So I usually tend to say it was an elastic collision. I'll pause if I can. Angles? Oh. See, hopefully you're appreciating what I said a couple of days ago when I said, if it's a nice straight line, just letting right be positive and left be negative and be able to just divide and get there. And okay, let's delp. Do I know what the initial momentum of object A looks like? Looks like that. How big? Mass times velocity. 12.1 times 9.3. Don't round off. 112.53. Bam! They collide after the collision. Momentum A looks like that's the big circle. It looks as a picture from my picture, like that. Did they give me the velocity? Kohei, they did. See it right there? So this line is going to be mass times velocity. 12.1 times 4.1. 49.61. Plus, well, they didn't tell me the angle for momentum B, but certainly according to the picture, Vikas, it looks like it kind of went that way. This is momentum of B final. Can you see the two things that I want to add together? Are they vectors? I got a hankering. I'd like to add two vectors together. Any thoughts on how I might want to do that? tip to tail, really, you don't say. I'm going to draw my triangle nice and big up here. Now, I told you I like to draw the easiest vector first, which would be the straight horizontal. In this case, though, I'm going to use the easiest vector to help me with my diagram. You see, I think as a picture, this is going to look like this. That way, 49.61. And then I'm going to go this way. Tell me when I'm going to stop. I went too far, I think. How do I know when to stop? Because I know when I add these two together, the answer is supposed to be dead horizontal, right? So I'm still using the easiest vector to figure out what my triangle looks like. It's going to go like this. Here's the momentum of object B final, and this is 112.53. I need an angle. Oh! I think this angle is fairly easy to spot. What was that? Where?
The top left one.
Yeah, because I notice vector A final next to a horizontal line gives me that. I'm pretty sure it's that. Yay. Also, do you notice, just like before, I have side, angle, side, and I'm trying to find what's across? It's cosine law. Just like here, I had side, angle, side. I'm trying to find what's across. It's cosine law. Just like here, I had side, angle, and side, angle, side, and I'm trying to find what's across from the angle. It's cosine law. Have I mentioned that it's almost always going to be cosine law? When won't it be cosine law? Patience. I said cosine law. Okay. Momentum of B final squared. Well, that equals 112.53 squared plus 49.61 squared minus 2. 112.53, 49.61 cosine of, is it 51? Did you have a question? Or you? Oh, yeah.
You couldn't actually do this if you would add the two vectors that the question you gave us, you would have them to compare, right?
No, if you subtracted them, because you could say, how would I get this by itself? How would I move this over? I would subtract it to there. And then I would say, how do I subtract vectors? I don't. What do I do instead? I add the opposite, and that would also get you there. Yes? We're going to get to that next lesson, Mr. Smarty Pants, but thank you. We're going to get there next lesson. Smarty Pants. You're good at anticipating where I'm going to go in about 3 examples. I love it. Okay? But yeah, you could also get there with subtraction. Here, because they gave me the picture, I figured it was easy enough for me to figure out what the missing thing looked like. If they didn't give me the picture, I probably would have subtracted my way there. And you'll get the same answer. Speaking of answer, 112.53 squared plus 49.61 squared minus 2 times 112. By the way, Smarty Pants from me is a compliment, believe me. Times, from me, 49.61 times the cosine of 51. Any typos? By the way, get in the habit of checking for typos before you hit equals, because it's lots of typing. What the? Oh, square root.
You're missing.
Am I missing something?
If you look at the
100. You know what? I am. I said check for typos, and I didn't realize a 1 didn't show up. Sheesh. Square root. You get 89.987. Yep. Of course, that's nothing to do with what I want to find. That's the moment. But okay, it's a start. The final momentum of object B is 987. Not what I want. By the way, I might say I gave this to you as a multiple choice question. I could certainly just say find the final momentum and quit. On the written, I'm going to ask you to take it the whole way. Or I could just say find the magnitude of the velocity and I don't care about the direction. Or I could just say find the direction, I don't care about the magnitude. That would let you take shortcuts and cut corners and skip steps. But I'm taking you the whole way here. Spencer, this is your cue. If I want to find the velocity and I know the momentum, any thoughts on how I might want to do that?
Momentum divided by mass.
Thank you. So it's going to be 89.987 divided by, I've scrolled down, what was the mass of object B? 12? I think that was, I think B was lighter, wasn't it? Okay, don't do that. .4, 3 sig figs. And if I had said find the magnitude only, we could quit. Okay. At. Ugh. I can't, Manny, find, that'll be useless, because that's nothing of nothing. That's something northwest of something north, you know, it's not next to a vertical or horizontal line. Doesn't help. You know what would help? This angle right here. Clay, what did you just do with your hand?
Make a Z.
Oh, are you telling me if I find that angle? Dustin, see it? There's my Z. Except please be careful. I don't want to call it south of west. I want to, this angle here is what of what? North of south, east of west, what of what? It's north of east, isn't it? I want to end up there. Isn't that start out going east and then go north of east? So just so I don't accidentally forget, I'm going to write that in right now. North of east. Now let's find the angle. I think I can do it right here. And yeah, it's going to be the sine law. It's going to be the sine of theta over 49.61. What's across from it? It's going to be the sine of the angle that I know over, momentum B final, which was 89.897. Hey, Kev, what can I do with that 49.61? Multiply it over, and then when I hit equals, I'll go shift sign at the very, very end. Okay. If you want to show that step, you can. If you're comfortable, since we've written out all the numbers, going 49.61 times the sine of 51 divided by 89.897. Isn't what 98? Oh, is it 9? I wrote it down wrong? Don't do that either, Mr. Duick. You'd think I could remember that because it's 987. That's like in some kind of an order, one might even say. Hey, I can fix that here. 98. No one noticed. Whew. Okay. Oh, shift sign of that. And although that's an angle inside the triangle because of the Z rule, that's also the same size as the mystery angle that I want, 25.4 degrees. North of east, even though the angle that I found was south of west, it's the same size as the north of east. That's two-dimensional collisions, my friends. Hopefully, Travis, you're seeing, if you go systematically, it really just builds on a logical conclusion from Physics 11. Hey, if there's vectors, you'd probably have to do some tip-to-tail work. Oh, and hey, if there's no right angle, knock, knock, who's there? Not Pythagoras. Cosine law. So, what questions, what's your homework? First of all, take-home quiz. You're going to get a lot of time to work on this. I was trying to give you half an hour. You're actually going to get 35 minutes. You can now handle number 6. Number 6 is very tough. Number 6, you know what? I'm going to take that back. I haven't done one where they're both moving before and both moving after. Number 7. Number 8. Number 9. Some of these answer keys I did really quickly. If you think I'm wrong, check with a neighbor, and if you both get the same answer, give me a holler. I made up a bunch of extra questions because I found kids needed more practice, and I was not showing enough work, but trying to crunch the answer keys in a hurry, doing most of this on all calculator, visualizing everything, and you can see this is about where my threshold starts to show up. I think I have a video for you, though, first.